Okay, let's start. So first of all, some housekeeping. About the lectures, this lecture and next lecture, you guys can sort of make a decision. I'm going to offer you two options. I can guess what you're going to say, so I don't really need to ask you this, but to take the responsibility off my back and put it on yours, I'm going to ask you. So this is, in pursuit of new paradigms, and we can go as quasi-crackpot as you like. So today we can spend some more time on sort of very, very speculative ideas where I'm not going to offer you anything concrete, but it might plant some thoughts in your minds. But that will eat up so much time that then tomorrow we probably wouldn't be able to do anything significant on supersymmetry. We'll do a little bit, but not anything in any great depth. Or we can sort of not do the crackpot stuff. It's not full crackpot. Not do the quasi-crackpot stuff and have more time to do a sort of a thorough discussion of supersymmetry tomorrow. Of course, I know what you're going to choose, but I just don't want it to be on my shoulders, okay? So option one, less Susie, more sort of speculative. Votes, okay, yes. Okay, thanks. That was just a formality. The second thing is, did anyone do the homework? Did anyone attempt it? Nobody? Okay. Well, okay, well, we'll come back to that later. The third thing is, who asked the CP problem? Okay, right. This was an amazing question. And I've discussed it with the other lecturers and the organizers and so on, and who've offered me responses, none of which I'm very convinced by. So I'm going to give you my response, which I'm also not very convinced by, but it's a very non-trivial question. The question, if you recall from yesterday, is, well, pions are CP odd, and they're PNGBs. And so how can we have a Higgs that's a PNGB that is CP even? And this is non-trivial. The sort of highfalutin answer would be something along the lines of that C and P are, once you extend, one can choose a convention for them within the standard model, but once you extend the standard model with new symmetries, you have to choose conventions. However, and that can muddy the waters. However, there's something that is not ambiguous, which is that the pion couples to FF tilde when it decays to photons, and the Higgs couples to FF. Okay, and so, yes?
So could you fix the CP even problem by having the extended Higgs bring vector symmetry instead of axial symmetry?
Right, exactly. So this is Nathaniel's answer. So yes, so the symmetry breaking could have a vector current, and then it's very clear that you will be able to assign a CP even property to it. But more practically speaking, the interactions that are most relevant for a PNGB like Higgs are the ones that are breaking all of that lovely global symmetry that you had in the first place, for which you had a PNGB, which is the top Yukawa, the electroweak gauge interactions, and so on. So when you've already done that, you're already doing violence to the CP structure. If it had wanted to be a CP odd scalar, and you're coupling it like the Higgs to a pair of quark to the tops, you're already sort of forcing it by the standard model conventions to be CP even in that interaction. And that interaction, is a big breaking of the global symmetry of which it was a PNGB. So I think that partially answers the question, but it was a really fantastic question. So I hope you're satisfied. You can continue to bug me about it later. If you wish, I'd be happy to continue discussing. Okay, so we're just going to do 10 minutes or so to wrap up this PNGB story, and then move on to a completely different set of ideas. Again, I'm trying with these lectures to sort of expose you to sort of both the pursuit and the new paradigms part, in the sense of I'm trying to expose you to things that are sort of relatively new, maybe sort of slightly unfinished, but might point in new directions. And so we'll have a lot of material on that front to come in the remainder of this lecture. The last thing I want to do is shamelessly plug my own research. So I feel like really in an unbiased manner that I would present this if someone else had worked on this, but it just so happens that myself and some collaborators have been thinking about something along these lines, where we ask the following question, motivated by the standard model. when you look at the pions in the standard model, they have sources of explicit symmetry breaking that are completely separate, right? The pion, the explicit symmetry breaking that leads to a potential for pions mainly comes from the quark masses, but as we've already discussed, it also comes from the fact that QED exists, from gauging the fact that the pi plus minus coupled to the photon. And morally speaking, these are sources of explicit symmetry breaking that are completely separate. They don't know anything about each other. There's no relationship between the QED gauge coupling at the GeV scale and the mass of the up and down quarks, okay? And so the question then, I think an interesting question then is to ask, when we've been discussing these PNGB Higgs models, we've only actually considered the sources of explicit symmetry breaking of whatever the global symmetry was that we are absolutely forced to have, right? Because they're there and we measure them. If the Higgs is a PNGB, it still has to couple to the top quark. It still has to couple to the electroweak gauge bosons. And so those are irreducible sources of explicit symmetry breaking that we absolutely have to take into account. However, that does not forbid there from being additional sources of explicit symmetry breaking in the UV that might also modify the potential. And so it's a reasonable scientific question to say, well, what if just like with the pions, what if there's some other non-IR interaction source of explicit symmetry breaking? How could that potentially change the story? And what it would do, I'm just going to parameterize it. I'm going to try and move through this relatively quickly. You can parameterize this source of additional symmetry breaking, explicit symmetry breaking, with some small parameter, epsilon, small with regard to, let's call it dimensionless units. There'd be some expurion field that is in an irrep of the global symmetries. Okay, this harking back to thinking about dipoles, buckyballs, so on. And so it's in some irrep. It'll be in a symmetric irrep because it would have to be able to couple to this nonlinear representation of the global symmetry. So for instance, this would be a representation of SO8 for a twin Higgs model. And it has to be able to couple to n copies of the same field. Remember, this is the thing that contains the Higgs in it. If you remember, this was the thing with the e to the I sum over generators, that nonlinear representation, an. And if this were asymmetric, then you'd get nothing because the product of these guys is symmetric under exchange. So the only representations that will matter will be the symmetric ones, and then we just tie up the units correctly. I hope I did this right. Over f to the n minus 2, because this thing had dimensions of f, the symmetry breaking scale. You can calculate what scalar potential you get from this for the Higgs, and in the case of an SO8 symmetry, you get, if this spurion explicitly breaks SO8 to SO4 cross SO4. This was the pattern of explicit symmetry breaking we saw for the twin Higgs yesterday. Then the potential you will get looks like this. It's epsilon f squared, lambda squared, and then a function called a Gegenbar polynomial of cosine of 2h over f. You get the cosine of 2h over f because you recall yesterday. Yep. Is my writing too small? Yep. So sorry. So this is a subscript 1 all the way to a subscript n, and the same along here. Here there's 3 halves in the superscript, and here there's little n. Sorry about that, I'll write bigger. Pardon? Yes. Sorry, yes, that's tiny, yes. N minus 2, little n minus 2. Sorry about that. It's cosine of 2 h over f, because you will recall yesterday in the twin Higgs, because you've got the SO4 cross SO4, you tend to get cosine squared minus sine squared, which is cosine of 2h. That's where it comes from. This is a Gegenbar polynomial. Has anyone worked with or seen Gegenbar polynomials before? Yes, 1, 2, 3. Who has, oh, more than 3, okay, plenty. Who has solved for the orbital wave functions of hydrogen before? Okay, so you all are familiar with Gegenbar polynomials because that's what they are. If you were to solve for hydrogen in n dimensions, then you would be working with these guys. Or to put it another way, in 3 dimensions, this is just a Legendre polynomial, which got superseded, generalized by Gegenbar. Okay. And so these are fancy functions. The 2 things that you saw in the potential yesterday are Gegenbar polynomials. You know, the contributions you saw from the top sector just correspond to little n equals 1 and little n equals 2. Just like Legendre polynomials, because these are effectively Legendre polynomials, they look like this. They sort of have big wiggles. Look like that, as a function of h over f. And the neat thing is that the global minimum here, these are degenerate, the global minimum here is at values of h over f, which are proportional to effectively 1 over little n. So as n gets bigger, they want to have a minimum which is closer and closer to the origin. Now, do you remember the problem we were trying to solve yesterday is that the Higgs couplings tell you that v over f is small. But when we just had the contributions from the top sector, we had to fine-tune the different pieces of the potential in order to get a VEV that was small. Whereas this looks like it wants to do it for you for free. The reason that that would be natural, imagine this was just the only contribution to the potential. The reason that would be natural is that if your spurion is in this n-index irrep, this is the only thing you can get at leading order. So I can do as many loops in whatever the UV completion is. I can do loops in the IR. I can forget about loops and just write down everything allowed by symmetries. And this is the leading term you will get. So we say it's radiatively stable. In other words, it's natural. At order epsilon squared, you can have 2 k's, and you can start to tie together indices. So then you get things that go from little n equals 0 all the way up to 2n. But it's doubly suppressed by epsilon. So if epsilon is small, then those are small contributions. OK, so this is the idea. You can rerun the fine-tuning calculation from yesterday that you all did in yesterday evening in your rooms. And what you get is that the fine-tuning measure, remember we called it big delta, is now modified. We get 1 plus 2 sine squared v over f, you will recall that from yesterday, minus 2 g prime at, I'm not going to write in cosine of 2 v over f each time, but you can, that's the argument in there. And g is the Gegenbar polynomial. I'm just going to drop the superscript and the subscript. And then what you will recall, again from yesterday, 2 sine squared v over f, all multiplying 1 plus 2g double prime. So recall this is, we're including the old contributions from the top sector. Yep. No, you could have, you're not forced to have anything. We're trying to make a guess. So the guess here would be that the UV completion, whatever it is, has one source of explicit symmetry breaking that's in a non-minimal irrep, n is not 1 or 2, and that gives you a leading contribution. But you're not, that you could have the other ones, as I said, you will generate the other ones at order epsilon squared and so on.
It's always, so if I have n equal, sum of n equal 1 and n equal 2, will it always be less?
Not necessarily. So the n equals 1 and n equals 2 you actually already have from the top sector. That's what it gave you. So we're just saying, suppose there's some additional source of explicit symmetry breaking, and this is what it would give you. But we're not forbidding the other ones. You could have all of them if you want, but then the only condition is that one of them is sort of dominating by someone might be like 10 times bigger than the others or something. But yes, there's absolutely no symmetry that is forbidding the other ones.
Is that how we define this totalitarian principle that everything that is not forbidden should happen?
Yes.
How are we sure that the Higgs function is?
Very good. This is a really excellent question. So the question was, I said on Monday, I mentioned the totalitarian principle that everything is not forbidden should be included. That's absolutely correct. But that doesn't mean that, so that's a very, very good point. But there's an additional component, which is that the epsilons get carried along with things. So indeed, not everything, I should include everything in terms of symmetries that if I have this, that then is also allowed. But K carries an epsilon with it. So I can write down all the other operators, but the only thing that I need to have by the totalitarian principle would be the epsilon squareds and then the other irreps you get from putting together 2 of these irreps. And then epsilon's cubed and all the irreps you get from putting together 3 of these irreps and so on. That's what's required because they are allowed by symmetry. You might say, well, surely I could have other ones with a different epsilon that's maybe bigger, and that's also possible. But we're making a guess about what is, we call it technically natural. We're making a guess, assuming that this is the leading source. It's sort of like with the pions. If you look at the pions, QCD has, in the UV, it has 2 spurions that explicitly break the symmetry, QED gauge coupling, and the quark masses. Those spurions are in an irrep of SU2 left cross SU2 right. And then you write down everything that's allowed. There are actually corrections to the pion mass that go like m quark squared. There are ones that go like e to the 8. They're there, but they always carry along with them either m quark or e. Those are the epsilons in that case, and that's the same argument here. But it's a very good pertinent question you ask. Yep.
Is that a 2n on top or a 2h?
Sorry, that's 2h. I apologize. That's 2 Higgs. Yep. Okay, so this is the fine-tuning evaluated at the minimum of the potential. So you assume that you've picked all of your coefficients in your potential so that you get the right V over F, and then you ask how much, if I were to change one of those terms by a certain amount, a fractional amount, what fraction would the Higgs VF change? And you will recognize all of this from yesterday. But the interesting thing is if this is sort of dominating or almost dominating the potential, then the point, you will get the right V over F somewhere around here. At that point, G prime is small because it's a local minimum. So you can forget about this G prime. Sine squared, if V over F is small, sine squared of V over F is a small number, so you can forget about this thing. So you ultimately get what you had yesterday. I'm going to go too low if I go that way. Which is that yes, sorry. Okay. Something that goes like this. So 2 sine squared V over F 1 plus 2G double prime. Okay, now, if you recall going from the sort of minimal style PNGB Higgs model, we went from 1 over sine squared V over F, and then we went to the twin. We got 1 over 2, so things were getting better. The fine-tuning was smaller. Here we get that, but we get a new correction, which is 2G double prime. Now, G double prime is the second derivative here. So if this is a rapidly oscillating function, G double prime is big. You see here that if you think of like differentiating cosine of nx, right? Cosine of nx is just like somewhere between 1 and minus 1. The second derivative of cosine of nx is n squared, between n squared and minus n squared. And so if n is like 10, it's a factor of 100 or something like this. So that's essentially what's behind this, what this could buy you in terms of making fine-tuning a bit more palatable. And indeed, these Gegenbaur polynomials, if n is reasonably large, like say 6 or 8 or 10 or something like that, this is a big number. This becomes like 36 times 2 or something, or 100 times 2. And this can in principle, significantly alleviate the fine-tuning. It doesn't help with the fine-tuning of the Higgs mass. This is for the VEV. It doesn't help with the Higgs mass. So overall, these theories are only like 4 times less fine-tuned than a naive model without this structure. But I think they're sort of interesting. They, of course, leave big questions, which are sort of related to your question, which is, well, that's all well and good, but why would nature do this? And that's, I don't know. I try to be agnostic and to inject as little of my personal aesthetics as possible into my model building, because it just has not served us well to do that. But it's still a very real question regarding these models. Okay, so I would like to now move on to something completely different. So if anyone has any questions about this or more broadly about any of the PNGB Higgs stuff, then speak now or forever hold your peace. Yes? Almost. Yes?
So I guess if it helps with the fine-tuning in the VEV, but not in the Higgs mass, could I also think of that as like a fine-tuning in the quartic? Or,
Yeah, so indeed. So at lowest order, yes, sorry, that's a good point. So the question was, if it helps with the fine-tuning in the Higgs VEV, but not the mass, can I think of it as being a fine-tuning in the quartic? And indeed, that's a useful way to separate these things up, usually. You know, we have two parameters, V and M Higgs, and we have to predict both of them from whatever the UV completion is. And they have to be calculable, otherwise, well, we'll come to that. And so you can relate, in the standard model, you can relate that to the big M squared, up in front of the big Higgs squared, and the quartic. And so you can think of then one as a fine-tuning in the quartic and vice versa. Here it's slightly different, because actually because these functions are oscillating very rapidly, you can't ignore the higher order terms. If I were to expand this to like the quartic, I also actually have to include, to really reproduce what's going on, I actually have to really include Higgs to the 6 and Higgs to the 8. So that for standard PNGB models, what you say is correct, essentially. But for this sort of model, you need to think beyond the quartic. Yep?
can you explain a little more precisely what you mean by calculable?
Calculable. So you can take QCD with finite quark masses and calculate the pion mass. So we will come to that, but this question of calculable is really at the core of why we worry about naturalness. Calculability is everything. This is the reason the standard model, there's no hierarchy problem in the standard model, right? The standard model does not predict the Higgs mass. It's just an observable. You have to do an experiment, measure the Higgs mass, and then whatever scheme you like, that fixes a parameter in your Lagrangian. There is no hierarchy problem in the standard model. The only problem, the hierarchy problem comes about because the standard model has to be UV completed. And then these parameters should be calculable from within that more fundamental theory. Okay, any other questions? No, okay, right, now we go crackpot. So that was everything I've shown you so far is a symmetry-based approach, right? We're playing with global symmetries here. If we had time, and maybe we'll have some time tomorrow to do supersymmetry, that is also a symmetry approach. That's a space-time symmetry. And you've seen what happens. So now we want to ask the question, how, first of all, in pursuit, i.e. you haven't arrived there yet, so you're trying to find out what the new paradigm is. If we were to go beyond symmetry, what are the possible options? As I alluded to in the first lecture, obvious examples would be if you have some notion of plenitude, we will come to something like that, or some sort of feedback that is sort of dynamically pushing Higgs parameters towards critical values that are small relative to the other length scales in the problem. But before we get there, I'm going to sketch some sort of slightly more wacky observations, and then we'll start to talk about cosmology. So we want to understand why one could have m Higgs squared, for instance, much, much less than the scale at which the standard model is UV completed. As I've sort of tried to hammer home, the hierarchy problem only exists if the standard model is UV completed, which we think it is, or it must be. So we want to explain this. There are some logical possibilities. One, which is timed incredibly well with the question, is that perhaps the Higgs mass is never calculable. So suppose whatever the full true UV completion of the standard model is, it has free parameters which are like the standard model. You can only fix them by experiment in principle. And that from within that theory, you could never calculate what the Higgs mass is. Then, in principle, there'd be no hierarchy problem, right? The problem there is that we can't pick and choose. So if we're really going to suppose that reductionism, calculability is essentially the progress of reductionism, you can, in principle, calculate the existence or the properties of elements from atomic physics and nuclear physics and so on. As we go to shorter and shorter distance scales, we find theories, we find layers of effective field theory from which we can, if we zoom out again, we can calculate the longer distance physics. This would mean that that entire endeavor has terminated now. And so we have to, if we were to take this seriously, we have to take everything that it gives us seriously. So questions of flavor, structure, baryogenesis, all of these sorts of things would then be called into question, right? The reductionism would be over. But nonetheless, this is a logical possibility. I don't know, Nathaniel, is there anything that can rule out this possibility? No. So yeah, if this is the case, I guess.
Reductionism is over when you find the particles that are truly elementary, right?
Well, so the point was, this is good. The reductionism, the comment was that reductionism is over when you find the particles that are truly elementary. To be honest, I think the ultimate conclusion of reductionism is probably not going to be a set of particles like the Standard Model. Right? I think even thinking of particles doesn't work when you include gravity and think about very high energies. So it would likely be something even more bizarre. I'm inclined to say string theory, but I'm also very agnostic. As I said, I'm a bottom dweller. And so while I listen to string theorists, I wouldn't necessarily marry string theory myself when I think about the deep UV. I'm very open-minded, but I imagine it wouldn't be something like the Standard Model where you write down a bunch of particles. Yes? No, sorry, I thought you were...
The good thing about marrying string theory, is, which I did, is that you can still see all sorts of other theories.
Yes, yes, yes. If you knew me, you'd know that's not my style. But okay, so inseparable scales. This is a little bit more concrete and comes essentially under the moniker of UV-IR mixing. By the way, there are two things I'm about to discuss, for which Nathaniel is definitely better qualified to tell you about. So please, Nathaniel, if you want to add something here, then do so. But pardon? Yes, exactly, exactly. I'm not going to repeat that comment. So what is this? So we call what I've sort of described this sort of effective field theory approach of going to longer and longer distance scales. It's deeply tied to the separation of scales. If you have a theory that's valid at some short distance scale and you want to know what the long distance predictions are, you use effective field theory and use an appropriate theory at that long distance scale. For instance, you would be absolutely bonkers to try and calculate the electron, let's call it the electron orbitals in hydrogen, the wave functions in hydrogen, starting from the fact that you know that the proton at the center is made up of quarks and gluons, so you start from the QCD Lagrangian, right? That would be bonkers, right? We use the effective description at the appropriate description at that length scale, which would involve the proton as essentially a point particle with some spin and charge, and forget about QCD for that purpose. But you can only do that if you have a well-defined way of separating the relevant physics on different length scales. We call that essentially Wilsonian, because Wilson was a pioneer of effective field theory logic, and he sort of figured these things out, along with other people as well. But we call it Wilsonian. But the fact that we can do that actually rests very fundamentally on some core principles of quantum field theory, which include unitarity, so probabilities add up to 1, locality, causality, and for high energy physicists, Lorentz invariance. But it's possible that you could imagine the full fundamental theory actually violates one of those assumptions, one of those words I just said there. Then it's possible that that you can no longer separate scales in any robust way. And we call this UV-IR mixing, essentially that you can't decouple these two questions. You can't integrate out the short distance physics and just work with the EFT at the relevant distance scales you're talking about, because of UV-IR mixing, you would have to appeal to what's going on in the UV every time you calculated something that's going on in the IR. I.e., if it were hydrogen, you would actually have to, and this happened, you would actually have to include the quarks and gluons every time you wanted to calculate the electron orbitals. That's an analogy, by the way. And so what could such a theory look like? It's actually not, you would think I can't even write down something that looks like a quantum field theory, but you can actually write down things that look very, very familiar, very much like a quantum field theory, which have these properties. So for instance, if I take a massless scalar field with a shift symmetry, I can write the kinetic terms. And a term, the next leading term in the effective field theory would look like this, something like d mu phi all squared. This is a dimension 8 term. It turns out that if this sign is negative, which it is here, that this theory does not have a unitary local causal UV completion. Okay, you can see this, the most robust way to see this is by thinking about scattering amplitudes and dispersion relations. And so what this means is that if this theory describes nature, you'd have to start to approach the scale lambda. Yes?
So which assumptions are crucial to break here to have this UV-IR mixing? Like, do you have to break all of the unitary to
Okay, this is a really good question. So the question is, which of these sorts of assumptions do you need to break in order to have UV-IR mixing? I honestly don't know, because I have not seen a clean way. Once you break one of them, I have not seen a clean way of separating the damage you're doing to the theory. So here, this is manifestly Lorentz invariant, so not Lorentz invariance. But once you break something like unitarity, it's hard to disentangle that for me, in my perspective, from just breaking, like, for instance, causality. But I don't know, Nathaniel, do you have any clean way? Can we say that you just need to break causality to have UV-IR mixing?
Like I said, separate Lorentz violation.
Yeah.
You can break the Lorentz symmetry in a controlled way that doesn't, where you have a unitarity violence. Lorentz invariance is limited with observation. That's separable. For causality and unitarity, I mean, you can say, so you can say which thing gets broken, and it actually depends on the quantum mechanical vacuum used in quantized theory. So a classic example is, let's say you have a ghost, right, with a long side kinetic return theory. You could either say that has constant instability, right, negative energies, and therefore the vacuum decays catastrophically. That's actually how you interpret the Lagrangian if you quantize the theory with ordinary harmonic oscillators. But you could also do, Dirac taught us how to do indefinite metric quantization, where you instead your vacuum state is annihilated by the raising operators. And in that theory has a totally stable vacuum, this is stable lowest energy, but unitarity. And so actually there's, depending on the choice of vacuum, you can cleanly separate each of these. So
Right.
it's a little bit, it's always a game of whack-a-mole. You can't get rid of all the problems, but you can sequester consequences in one direction.
Thanks. So yes, I guess the answer, just for the recordings. Yeah, well, I'd say that I'm going to... I'm not as eloquent as Nathaniel, so I would just say that the answer to the question of, which is broken is a question of how you define the quantization of the theory. So you can define it, like Nathaniel said, in such a way that what you see is causality violation, or you could define the way that you quantize this sort of weird theory such that you see the violation as unitarity violation. This is an excellent question. Another place that this would show, so this theory, you can also see, but the thing that's sort of compelling is that this is sort of a sick theory, right? It's going to violate our fundamental principles in some way, but it's sort of compelling, right? Because you, in principle, at first, a very, very naive first glance, you need to start to approach these energy scales to sort of see that sickness. Of course, that's not always true because you could have vacuum decay down to infinitely low energy and things like this. But it's sort of a compelling thing to think about. And some of you may be familiar with another example, which is known as Lee-Wick, where you can essentially have propagators for a scalar particle, for instance, which looks like this: 1 over p squared minus m squared minus 1 over p squared minus, let's call it m tilde squared. And so if m tilde is much, much bigger than m, the mass of the particle, then at low energies, you just essentially see this propagator. But then at high energies, you see that these two, as I go to really large p, the two m's become irrelevant, and this thing goes down to 0. And so this was developed in a time when people were very worried about renormalizability and so on. But it has sort of become reincarnated as a classic example of a type of theory which is sick, right? It's got a ghost. The sign of this pole of this propagator is wrong. I'm going to carry on, but I would just say that you know. Some other examples that Nathaniel's worked on, for instance, is non-commutative geometry, where you can have sort of microscopic Lorentz violation. That's another example. And I think Nathaniel would agree with me here. Nothing that's been written down trying to explain naturalness or attack naturalness along these lines is fully satisfactory in some way. However, I think so this is why we're sort of going quasi-crackpot here, but however, I think it's very, very intriguing, and I can't help but think of the sort of conversations that occurred around the time of the discovery of quantum mechanics. And some people still have those conversations, right? Where people were saying, but no, it's not, this is not what happens in classical physics. And then one had to realize that actually the quantum mechanics is the fundamental thing, and the classical mechanics is the emergent thing. And so I sort of wonder, I'm just being I'm speculating here, but I sort of wonder if we have similar like mental roadblocks that maybe we can abandon one of these fundamental principles. It appears fundamental to us at this moment. And we will end up with a theory that to us, as quantum field theorists, looks sick, but once we learn to work with it and to understand how to work with it, maybe it could explain something. So I'm sort of, I wouldn't say I'm optimistic, but I'm hopeful that maybe we will find something someday along these lines, which is within a self-contained, non-pathological framework, even if it looks pathological to us at the moment. Okay. The next interesting set of ideas that might have something to do with naturalness that has not really been concretely tied to the question of naturalness involves swamp monsters. And this is to do with the idea of the swamp, a set of ideas known as the swampland conjectures and so on. Who has heard of the swampland? Wow, was it in these lectures? Was it in Tassie?
Just a funny name.
The swampy PR is very, very effective. Okay, so great. So you know all this stuff. So what's the idea of the swampland? So the idea of this.
Something is not the same as knowing about something.
Yes, for sure.
It's not the first time I've heard a lecturer ask, "Have you heard of this?" And people say yes.
Yes.
And the lecturer says, "So you know this."
Yes.
Not the same.
Well, I have also heard of it, and I also don't fully understand it. So, so we're all in the same boat here in this case. But the idea is the following: that if you were to take the set of all consistent, hypothetical theories of quantum gravity and the UV, the very interesting, I think, speculation, which is way more than a speculation, right? There are some, for certain aspects of this, there are some very robust calculations and arguments. So please don't, this is less, in some sense, speculative than this stuff. The idea is that they all flow into effective field theory, so quantum field theories, in such a way that if you were to go, this is the UV, we go down to the IR. Go down to the IR. And the idea is that if you were to take the set of all self-consistent 4D quantum field theories, effective field theories, that is bigger than the set of all 4D quantum field theories you could get from as the IR limit of a self-consistent quantum gravity theory. So all of this can come from quantum gravity, and all of this is the swampland. And this is all EFTs. Possible. So this is quite a profound sort of observation in some sense, and it's very similar to this, right? This looks like, to all intents and purposes, like a perfectly okay effective field theory, but actually it's not. It's sick. Whatever's in the UV is not a quantum field theory. And this is sort of a similar argument, right? That you could have theories here that are perfectly consistent as quantum field theories, but could never, ever have come from a theory that accurately describes quantum gravity. Now, there are some arguments for this. I'm going to sketch over them. I don't find them totally foolproof, but they can give you a sense of where they come from. So one example would be, imagine if you have a, which concerns global symmetry. So the idea is that quantum gravity violates all global symmetries. That violates, you know, that word does not quantify by how much, okay? So the quantum gravity might violate all global symmetries, but only by a small, non-perturbatively small amount, or it might violate them by a large amount. That's more open for debate. There are lots of interesting works on that front. But the idea is that you shouldn't have any global symmetries. But those, you could have approximate global symmetries, like U1 B minus L would be an example. In that deep IR, in the standard model, B minus L is an approximate global symmetry. But you would expect by this argument that quantum gravity violates it. And one way of seeing this is that imagine you had a global symmetry, and you had a black hole, you produced a black hole charged under that global symmetry. If it were in a Hawking radiation, can't carry away, imagine it's just photons, it can't carry away global symmetry charge. So if you had a true global symmetry, say Q not equal to 0 under some global U1 or something like this, then you would have black hole remnants. You'd have microscopic black holes that can never decay because the Hawking radiation can't carry them away. So you'd get left over with black holes that are stable remnants. And there are arguments, cosmological and otherwise, against such things. As I said, that's not a fully, I'm not giving you a proof here. I'm sketching the arguments that lie behind these things, but I'm not going into great detail. Another one is known as the I'll tell you the electric weak gravity conjecture. According to the electric weak gravity conjecture, gravity is the weakest force. There are actually a few gravity is the weakest force type conjectures. You could actually derive the relevant results just by comparing the force between two charged objects. Imagine you had some gauge force, and you would want, for instance, the Coulomb repulsion to be stronger than the gravitational attraction, and then you can actually derive this. Another way of deriving it is, again, to think about black hole decay. Suppose you had an extremal black hole of charge Q, now under some U1 gauge symmetry. If it's decaying, if it's ultimately going to decay away to nothing, it has to be able to Hawking radiate particles that carry away that gauge charge. The mass of this extremal black hole, I'm working in units where I'm going to separate the gauge coupling out from the charge. That's not conventional, but it helps me. The mass of this extremal black hole would be Q G M Planck. And if it's going to be able to decay, then there has to be, say, by emitting quanta that carry charge little q, then because we can just look at the ratio of big Q and little q, the number of quanta that it has to emit of charge little q to be able to decay is just big Q over little q. And so the mass of those quanta, it has to be able, that mass has to be sufficiently large that it can access all of those quanta, right? So there's an upper limit on their mass, which you can derive, which would be that m, big N, is less than this mass, which then ultimately leads to the conjecture that m of those quanta, the mass of those particles, is less than g q m Planck. In other words, the spectrum of all of the physical states in nature, however it's realized, has to include quanta of mass less than this. Otherwise, you would get, again, a stable charged black hole that can never decay. There are much more robust derivations of this result. And if you would like to know what they are, I'd be very happy to point you to Nathaniel for references. Yes?
Why is it bad if they can't decay?
This is the question. So the question is, why is it bad if they can't decay? This is why these are not really the most robust. I'm giving you the arguments that are. It's a really good question, and we were discussing it yesterday. It's a really good question. The more robust arguments are more theoretical and don't rely on this black hole remnant argument. But nonetheless, you can imagine. So one, if you just think about cosmologically, you would expect to, we will have you would expect to produce lots of little black holes, say when the universe reheated, and you could produce these things and they would be floating around, for instance. So you might have observational limits. But it's not so clear. I'm not going to give you a robust answer to your question, but it's a very good one. Maybe tomorrow, just like with the CP question, I can come back with something a bit more convincing. Yep.
Why is it that the global symmetry and gauge symmetry stories are different here? Like, why can the gauge charged black hole decay by emitting charged particles, but the global symmetry charged black hole can't?
A very good question. So the question is, why are these two different? So here, if there were an exact, so you could, it's to do with really the mass. I mean, so here, for an extremal black hole, the mass depends on the charge. Whereas here, you might get all the way down to having just a Planckian mass, and the mass doesn't depend on the charge. So you don't have a similar sort of argument in that case. But indeed, you might say that you should be able to have, so say you have big Q, and you don't know what big Q is. You could say, well, maybe then there should exist particles of little q, such that if with mass, little q smaller than m Planck, so that you can decay to those. I think that's a logical possibility. Yes.
Throw something out. I'm not aware of solutions to general relativity with global charges. Right? So there are solutions to GR with a U1 gauge field that have electric field lines coming out of the black hole and Gauss's law that promises you that charge is in there and conserved. But there's no analog for a global symmetry. And black holes, when you poke them, they settle down to configurations of just the conserved charges. So if you threw a lot of global charge in there, I would expect it to settle down to something that didn't have the global charge in, and then radiate without the global charge.
But you see, to me, there seems to be a loophole, because I could take G to 0, and I recover a global symmetry, because that's just the ungauged case. And then as long as I have a massless particle that has no charge, a massless particle that carries charge under the global symmetry, then perhaps it could decay to it. And indeed, there are no global charged black hole solutions in GR.
If the black hole has no global charge, then it's under no obligation to Hawking radiate into something with any particular global charge. It can Hawking radiate into things without it.
But the thing is, I could have started with an uncharged black hole, and I drop one quanta that carries global charge into it, and then it's a global charged black hole.
Is it? I can't tell from infinity.
Right, but this is what leads to this argument. You could, from infinity, if the global charge was conserved, this is the point, because the straw man is that gravity does. You break the straw man is that gravity does respect global symmetries. And if it did respect global symmetries, I could take a standard black hole, drop one charge in it, and then it is a global charged black hole. And then it couldn't decay.
Yeah, I think these are sort of slightly different ways of motivating.
Yeah. Yeah.
What would stop a global charged black hole from just radiating a global charged particle, just like the gauge charge? Wouldn't you just get a similar mass constraint globally?
Yeah, I mean that's this limit of G go to 0, which seems to be a potential loophole. If you had a massless quanta, then it could eventually decay away all of that global charge. But as I said, these arguments, these are not the most robust ways to frame these things. I thought they'd be the most accessible, but you're poking loopholes that exist. Okay. Now, but suppose this is true, which it very plausibly could be. Then you might say, aha, this is something very, very non-trivial, right? Because it ties together a mass scale for states that must exist in your theory, and a gauge coupling and the Planck scale. And so there are very interesting speculative ideas to apply this to the naturalness problem, because suppose the Higgs, now it's not going to work for hypercharge because hypercharge is just too big. The constraint would be that the mass is like less than 1/10 of the Planck scale, which the Higgs trivially satisfies. But suppose you had some extremely small gauge coupling, some extremely small U1 charge. Then you could make an argument that the mass, and suppose the Higgs carried some tiny charge under it, that the mass of the Higgs had to be much, much smaller than the Planck mass. Otherwise, the theory could never have come from a consistent UV completion involving quantum gravity in the first place. Sounds a little bit too good to be true, and it sort of is. There are details, and it's not so straightforward, but it's a very interesting speculation, and I think maybe something valuable will come out of that. Yep.
So do you see the gauge coupling, right?
Pardon?
Do you have inequality
Yes.
in gauge coupling?
Yes. Yes.
When we say weak gravity conjecture, often people say that we are comparing that.
The charge. Pardon?
The gravity is like weak in comparison with the other.
Yes.
How we can see this?
So look at the force between two of these particles, like the Coulomb force between two of these particles, and the Newtonian force between these two particles, and you see that if gravity is the weakest force, you satisfy this. So normally, right, when we look at the Coulomb force, we use E, but we've really packaged the electromagnetic gauge coupling into what we say is E there. So that's why I'm carrying it around, because
So if I write the new gravitational law here, I'm gonna see that G gravity is less than.
yes, exactly. So if you think you've got with Newton, you have m squared over m Planck squared, and then 1 over r squared. And with Coulomb, you'll have g squared q squared, and then it falls out. Yep. I'm sorry, I haven't given a very convincing argument for these. I can point you to references or people to discuss it with who will give you much more convincing arguments if you're really interested. Okay. Another place, and I'm going to offer something even less concrete. As I said, I'm trying to sketch the in pursuit of new paradigms. All of these things I'm discussing would represent a new paradigm. Here I've really nothing useful to say, so I'm just going to say some buzzwords and speculate, which is that we're really, we had what I showed you before with the PNGB-like Higgs. That was a symmetry-based approach to understanding naturalness. There's a bit of a renaissance occurring at the moment in terms of how we understand and frame symmetries. You may have heard of higher form symmetries. These would be symmetries for which the conserved current isn't necessarily a vector. J mu would be the conserved current for like a U1 symmetry. This could be something like J mu nu, a 2 form, or even something higher, J mu nu omega, something like that. Non-invertible symmetries. These are symmetries that don't form a group in the usual way. Once you do basics of group theory, you have an inverse, which is essentially that you can invert. These don't have the sort of canonical group structure, but they have been observed to play a role in understanding certain properties of quantum field theories and so on. And so this is very exciting and interesting. And another one that comes up that I think is very interesting and not as many people are thinking about is subsystem symmetries. So these are symmetries where you might have you would have a theory that is not a continuum theory, it's a lattice of some description. And there may be certain scales in that lattice, say when you include certain sets of lattice sites, where if you just restrict to that subset of lattice sites, the theory has a symmetry, even if that symmetry does not exist if you include all lattice sites. So this is a subsystem symmetry. It has connections to things like fractons and so on, and it's very cool. Nobody has, in my view, connected these questions, these sort of emerging structures in terms of our understanding of symmetries with questions of Higgs naturalness, but that doesn't mean it won't happen. And so I would say watch this space. Maybe there's something exciting will happen there. Something that is also discussed often is scale symmetry. So suppose the only spurion for scale symmetry breaking, if we're sort of forgetting about the running of couplings, suppose the only spurion for scale symmetry breaking was the Higgs mass itself. Then all scale symmetry breaking would be proportional to the Higgs mass itself, so it would naturally be a small number, right? Because there's no other scales in the theory. That's the basic question to posit. But just like with the notion of, imagine you just had you have a breakdown of reductionism, you have to take everything. If you make that assumption, or if you think that might be what's going on, you have to take everything that comes along with it. This would imply that there are literally no other scales no other new scales in nature. So you have to find a UV completion which is scale invariant, essentially, and this is hard. And I can use the pion as an example because if you recall from the pion kinetic terms, you had for the charged pion kinetic terms, like d mu plus I e a mu pi plus squared. Here, there's no scale symmetry breaking. Yet, this interaction here broke the shift symmetry of the pions and led to a mass correction to the charged pions. The reason for that is that there is a UV scale, and that was QCD. And you can't ignore it. You can't pretend it doesn't exist. So in this IR theory, in this part, even though there's no scale parameter, like a mass, that doesn't mean you don't get mass corrections to the pion, because there is a scale which is the UV completion, which is why I sort of tried to hammer home on the first day. You can't talk about an effective field theory and pretend that the cutoff is just some redundancy in the way you do loop integrals or something like this. They come as a package. And so the pions are within an effective field theory, and there is a UV scale, and that's why you get corrections to the charged pion masses. Okay, so I'm going to leave the crazy stuff there, and go to sort of slightly crazy stuff. So are there any questions about any of this? Or grumbles? Or comments? Yep.
I guess the scale symmetry thing, like, it's not clear to me how this is solving the hierarchy problem or something, because don't you now have to solve the converse question of, like, how do you get the Planck mass out of the Higgs mass?
Right, exactly. So you have, sorry, the comment was, how could this really work? Because then you'd have a sort of inverse problem. If the Higgs mass is the only mass parameter, the only breaking of scale invariance, then where does the Planck scale come from? Indeed, you need a UV completion of gravity, which is scaleless somehow, and the Planck mass would have to be emergent only in the IR in some way. I'm not presenting this, by the way, because I think it's a promising direction. I'm presenting it as one that you will see sometimes, and the essential loophole, as far as I can tell, which is that you can't ignore UV scales if you appeal to this. It's not something, you see, you can do the ostrich thing and bury your head in the sand, but only for so long, because you're going to stop being able to breathe. And that's what happens here. You can pretend that the Planck scale is the only scale in the theory, for many orders of magnitude, let's say all the way up to 10 to the 16 GeV, but that feels like it's a very long way away. We don't need to worry about it. It's such a small distance scale that we'll never access it. But no, you can't. You have to, if you're going to take it seriously, then the full theory has to have no other scales in the UV. And so you have to write down that UV completion. If this is being recorded, so I apologize to any friends who work on this, but that's, okay. Former friends, yes, okay. Okay, so we have 15 minutes. Oh, yes.
Yeah, so I have a question about something that I understand. So maybe a very silly question. When you talk about subsystem, you mentioned about having a lattice.
Yes.
Different scales. Is that somehow, could that be related to E8 cross E8?
To E8, wow. So the question is, could the sort of lattice in the subsystem symmetry story be related to E8 cross E8? I don't see a connection. As far as you're talking about the E8 that comes from string theory cross E8. I personally don't see a connection. To be honest, I've not seen any subsystem symmetries or something that show up in condensed matter problems and have some utility there. I've never really seen anything that sort of corresponds to like particle physics, never mind string theory, that where it shows up. But it was a very good question. Any other questions? Yep.
Yeah. How does SUMLab helps you with the natural language problem? It's not the same to say that the parameters are just.
Well, so as I described, imagine, so this is a rationale for why you might need to have light particles. So suppose this is a hypothetical possibility that has been studied by people like Cliff Chung, Nathaniel, Isabel Garcia, and others. Suppose the Higgs is charged under some very weakly coupled U1 symmetry, like a tiny, tiny, tiny charge. Then it would have to, the Higgs would have to satisfy. If that's the lightest particle charged under that symmetry, it has to satisfy this. So it's giving you a rationale for why the Higgs would have to be light. What I said there is very quick. There are details, and details matter. But that's how, in principle, it could help understand it. Any other questions? No. Okay. So we have 15 minutes. I'm going to go into a new topic, which is known as self-organized. I'll do US spelling for you. Criticality. Okay, so as I said, alluded to in the first lecture, I made this analogy with transition edge sensors. So what is a transition edge sensor again? This is a system where you have a superconductor. This is the resistivity. Let's say 0 is along here. And in the lab, you set up some smart electrical circuit, which always fine-tunes the temperature such that you're sitting here. We call this the critical point, right? You're right fine-tuned at the point of phase transition. This would be like if you could have really good fine-tuning on your cooker hob, right? You could set, it wouldn't be very interesting to set the water to be, I can't convert to Fahrenheit, the water to be at 50 degrees centigrade. Constantly, that would be interesting, but it's not critical. But imagine you could fine-tune the cooker hob, so taking into account all of the environmental factors, the water sits at exactly 100 degrees, not centigrade, that is, so it's just on boiling point. That would be fine-tuning, right? And you can in principle do that. In the lab, you can do that with a superconductor so that you're sitting right here, and a small change in the fundamental parameters, i.e. the temperature, would lead to a big change in the resistivity, because if you just move from here to here, you've jumped in resistivity all the way up there, okay? And so one could draw an analogy and ask, because after all, if there is we say that fine-tuning and naturalness, another word you will hear associated with that is criticality, because if the fundamental scale in the UV completion of the standard model is big lambda, then you would expect whether the electroweak symmetry is in the unbroken phase or the broken phase, that the order parameter associated with that would be something like 0 or big lambda. But what we observe is that the electroweak breaking scale appears to be much lower than that. And so we say that the Higgs sector in the context of a UV completion is critical and fine-tuned, etc. So this raises the question, could you have something similar happen in nature, where this is the background value of some field? No, not temperature. Temperature is a field in a sense, but some background field. And the cutoff of the theory is lambda squared. So this is minus lambda squared, this is plus lambda squared. And this direction is mw squared, for instance. sorry, m Higgs squared. Oops, m Higgs squared. So this point here is the critical point. And so we can tune m Higgs squared to be very, very small compared to lambda by varying some background parameter. But if we were to change that background parameter by a small amount, then the value of the Higgs mass squared would change by a large amount. And this could be captured literally by that Barbieri-Giudice fine-tuning thing. If you set this up and you solve that equation, you would find that. Okay, so the question is, could the universe have done that? Right here, we have some feedback mechanism that's always pushing you towards there. And the question is, could there have been some feedback mechanism in the early universe, maybe during inflation, something like this, which was actually shuffling, maybe there's some light scalar field, shuffling the fundamental parameters in the theory around such that they get stuck at the critical point, even though it's fine-tuned. So this would be a fine-tuned standard model, but the fine-tuning would have happened for a reason. This is the basic notion behind self-organized criticality. And it turns out that I think this is a question that people thought about for a long time. People, cosmologists, people like Iad Valley, thought about. But there was sort of a revolution that occurred 9 years ago when Kaplan, Rajendran, and Graham wrote down a theory known as they called it the relaxion, which is a great name, I have to say, which was the first really robust example of a construction which does this, which actually fine-tunes the Higgs mass for you in the early universe. Just out of interest, who has heard of the relaxion? Okay. Who understands the relaxion? Knows how it works? Okay. Okay, great. So there are some basic ingredients. So let's go through the basic ingredients, the recipe. The first is that you are working, the standard model is in EFT. Don't need to say that anymore. The cutoff, by the way, I'm going to match their notation, so I'm not going to use big lambda here. I'm going to chop and change, but this, I'm going to match their notation so that if you're actually interested, you go and look at the paper, you should be able to map across. So the cutoff is m. Let's call it m. The cutoff squared is m squared, so let's call it m, sorry. You have some scalar called phi, weak typically, which has a shift symmetry. So if I shift, let's just say constant. At first glance, so we're going to build this theory up. At first glance, this scalar has a shift symmetry, so that if I shift it by some constant, the theory looks the same. Nothing changes. Then we introduce some explicit breaking. Which comes associated with some parameter, some spurion, g. I'm going to write it all in terms of of the low energy theory, but everything maps across to if this were PNGB. So say you had some spontaneously broken U1 symmetry, you would get a Goldstone boson, which would have a shift symmetry. If in the UV you had some explicit breaking of that U1 symmetry, then that would give you a potential for that Goldstone boson, which would be captured in the same way. So what I'm saying fits happily within that narrative. Okay, so then the action, the Lagrangian, for the CFT would be the standard model. There would be a Higgs mass at the cutoff is what you'd expect. And then terms like G. Oh, by the way, something that doesn't map across, and I don't know why they did this, is that they work in units where G is dimensionful. It is mass dimension 1. You can work in dimensionless units by calling a new parameter epsilon equals G over M. And you'll get all the same physics. It doesn't matter. It's just a choice of convention. But here, G is dimensionful. So you could have something like GH squared And in front of everything here, there's some unknown order 1 coefficient. Nothing should be unnaturally small or anything like that, but some unknown order 1 coefficient, phi, g squared, phi squared, and so on and so forth. And in general, they would have, you can write down the general form of these terms. They would go all the way up. You'd have higher powers of g in front of h squared and so on. You just have everything allowed by the symmetries.
You're missing a squared on the last term. Phi squared.
Ah, yes, sorry, thank you. Yeah, maybe I should put a half there as well, even though we don't even know what the coefficient is. Thank you.
Is it a plus or a minus?
Oh, whatever you like.
Okay.
Yeah, it doesn't really matter. We're going to pick a convention where the whole potential has, say, for instance, negative gradient. But that doesn't forbid some of these terms from being positive or negative and things. We'll choose a convention where there's some patch which is relatively large as compared to the allowed field values, in which the gradient is negative everywhere. But that's the only assumption we'll make about that.
My negative pointed towards or away from 0?
Like this. That's the way, so pointing in the usual way. Yeah. Okay. So far, this looks like a promising-ish theory, right? Because if there might be some field value phi where g phi is exactly plus m squared, and then you cancel the Higgs mass. But nothing's going to happen there, right? If you think, if this scalar field was rolling about in its potential, say you start off at the top of the potential and you let it roll down, there's nothing special will happen there. So, and this is, to be honest, if I had been trying to come up with such a mechanism, this is what I would have been playing with, and I would have kept getting stuck on the fact that there's absolutely nothing special about the critical point as regards this theory. The stroke of genius, however, was to add in an axion-like coupling. Phi over 32 pi squared f, I guess, where f is some allowed field range. G tilde G. This is the gluon field strength and the CP odd gluon field strength. And this is super duper special. The reason is so I can integrate this by parts. If I integrate it by parts, this becomes the same prefactor, but then with d mu minus d mu phi, some current. We call it the Chern-Simons current. It's a QCD current. And so you see here that this term actually respects a shift symmetry. So in terms of perturbation theory, no matter how many loops I might want to torture myself with calculating, this will never, in perturbation theory, this will never generate any corrections to the potential for this scalar field phi. However, as you will know from the axion, and we're going to cover this actually in a little bit of detail tomorrow, just to give you an axion primer, non-perturbatively, QCD from instanton contributions essentially at the QCD scale will generate a potential for phi. And so let's say non-pert. This will generate a potential for phi, which will depend on, which will look like m pi squared, f pi squared, cosine of phi over f. And just as a teaser before we finish, the magic that happens is that, as you all know very, very well at this stage, m pi depends on the quark masses. The quark masses depend on the Higgs vev. So this is the back reaction. This is the key ingredient. You will see you don't need to know how it works yet, because we're going to go through the details tomorrow. But this was the stroke of genius, because this is the thing that can make the point where g phi equals m squared 0 special. Because when the Higgs vev switches off, this coefficient goes to 0, the pion becomes massless, and so does the axion. Okay, so I think I should probably finish there. That's a little teaser for tomorrow. Are there any questions or comments? Yes? Yes, exactly. So the comment was that this makes it look like it's a CP even scalar, This makes it look like it's a CP odd scalar. CP is broken here. So you can think of G as being also, if you like, you can think of it as being a spurion that is CP odd, and so it's breaking the CP symmetry. Yep, absolutely. Yes?
If you also have the QCD axion floating around, does it still solve strong CP without interacting with this?
No, so indeed. So the question is, if you also had the QCD axion, would you be able to solve strong CP? The answer is no. If you adding another scalar doesn't work, because then you only have one QCD. So the potential becomes a function of both of them added just linearly. And so you will have one field then that doesn't get a potential from QCD, which is a linear combination. And you'll have what's left over here for the field that does get a mass. And for that field that does get a mass, as we will see tomorrow, the relaxion in its most basic form that I will show you, and we will discuss this problem a little bit, unsolves the strong CP problem. You actually predict an order 1 strong CP angle, but there are ways around this. We'll see this tomorrow. Yep. Phi could be dark matter. That's the question is, could phi be dark matter from a misaligned mechanism? Yes, it could.
Well, maybe we will call it here and head for lunch.
Thanks. Cheers.
See you at 2 for our inaugural talk from Mathew.
Yes.
About the last comment that you made.
Yes.